is pedigree analysis, and we're very familiar with this one as we have discussed this already. And of course, we will be applying all that we have learned about inheritances in analyzing pedigree. Now, first of all, we need to take note of the five major modes of inheritance, and this is very familiar. What are they? So the first one would be autosomal dominant. The second one would be autosomal recessive. The third would be X-linked dominant, and of course the fourth is X-linked recessive, and the last one would be Y-linked inheritance. So these are the inheritances that we would need to take note of in pedigree analysis. Now let's start with this by also being familiar with the different symbols. So don't forget all of this. Just try to remember. So the male is a square, female is circle, marriage is one line between a male and a female. Consanguineous marriage would be two lines. Affected males and females would be shaded. Carrier, but not always the case, would have a line or would have a circle in the middle, and several other things. You have to take note of that. So this you just need to familiarize with yourself with this. And then let's start off with the autosomal dominant. What are the major characteristics of this mode of inheritance? First of all, autosomal dominant traits appear equally in males and females. 1, 2, 3, 4, 5 females. 1, 2, 3, 4 males. So there more or less it's proportional, more proportionate, or more or less it's a 50-50. So almost equally appearing in males and females. And then unaffected individuals definitely not transmit the trait. And then if you have siblings that would have been affected, it's it would be it would imply that one of the parents would definitely be affected. And also one more thing is that they do not skip a generation. So autosomal dominant does not skip a generation. So all of the generations here are actually showing affected individuals. Example is Huntington disease, myotonic dystrophy, achondroplasia, and Marfan syndrome. So those are some examples of the autosomal dominant. Another one, autosomal dominant. Another one is autosomal recessive. In this case, since it is recessive, we would expect that it would skip generations. Another thing is that autosomal recessive traits usually appear equally in males and females, so that's why it's autosomal. So one female, one male, so equally males and females are affected by autosomal recessive traits. Again, skip generation. And then autosomal recessive traits are more likely to appear in progenies of related individuals. So if you see a consanguineous marriage, more likely it's pertaining to recessive or autosomal recessive. And then there's another one that you will notice that the male is affected while the parents are unaffected. This will truly show that it is indeed recessive. Okay, that's some of the important characteristics for this mode of inheritance. So examples is Tay-Sachs disease, cystic fibrosis, sickle cell anemia. These are autosomal recessive. X-linked dominant, of course, will be finding the dominant allele that produces the disease in the X chromosome, and the characteristics would be, first of all, it doesn't skip any of the generation. So generation 1, 2, 3, and 4 all have affected individuals, but notice that more of one of the sexes would be affected compared with the other. So let's look at the other. Affected males, first of all, affected males will pass the trait on to all of their daughters. So notice that the male is affected, and then all the daughters are affected, but none of the none of the sons. So this will indicate that it's X-linked dominant because the male will only pass on the Y. So, and the X would be containing the disease allele, the dominant allele. So all the female children would be affected as well. Okay, another one, affected females, if heterozygous, pass the trait to half of their sons and half of their daughters. So here's the heterozygous female, and then half of the daughters, 1, 2, 3, more or less half, and half of the sons will be affected, 1, 2, and then 3, so almost half. Okay, so this would be an example of X-linked dominant. All the generations are affected. One of the sexes will be more affected compared with the other. Example is orodigital or facial digital syndrome and fragile X syndrome. X-linked recessive, first of all, if you find these circles, it is showing you that it is indeed recessive, and then you just have to make sure if it's autosomal or X-linked. But in this case, all the males are affected. So since one of the sexes would be more affected, it is recessive, and then it is X-linked. More than that, an affected male does not pass the trait to his sons. So that is a characteristic of X-linked recessive. But they can pass the allele to a daughter who is unaffected, which means she is a carrier. And the carrier passes it to sons who are affected. So a carrier will pass on the trait to her sons only and not to her daughters. X-linked recessive, or at least phenotypically not to her daughters. X-linked recessive traits appear more frequently in males as compared to females. So in this case, 1, 2, 3, 4 males, and then this would be X-linked recessive. Now, why can't this be Y-linked? Although all of the males are affected, it's because of this. Because Y-linked doesn't skip generation as well. All the males in all generation would be affected. So since here is an unaffected male, it cannot therefore pass on its Y chromosome that is unaffected and then suddenly becomes affected over here. So it cannot definitely become a Y-linked. Okay, example of the X-linked recessive would be red-green color blindness. Finally, we have here the Y-link. All of the males would be affected here. All males offspring are affected. Y-link trait appears only in males. So it's quite the easy. This is the easiest to take note of. Okay, let's look at some examples here or some problem. Is the following autosomal or X-link? Is it dominant or recessive? Please explain. So since this one, the males are affected while the parents are not, it is definitely recessive. And then since males are affected and not females, then it is highly likely to be X-linked. So the answer to that is X-linked recessive because more males are affected and offspring show disordered trait but parents didn't. Okay, number 14 is the following autosomal or X-linked. Is it dominant or recessive? Okay, let's look at this one. So first of all, it doesn't skip any generation, so it's highly likely to be a dominant rather than recessive. And then let's look at this one. 1, 2, 3, 4, 1, 2, 3. There is an almost equal number of males and females that are affected. So it's autosomal dominant. 50% of males, 50% of females are affected. Both parents of offspring show the trait, and that is found in all generation. Number 15 is the following autosomal or X-linked, dominant or recessive. So since there are generations that are skipped, it is recessive. And then take note of this one. It skipped generation, therefore it is recessive. And more of the males are affected, so it is highly likely to be X-linked. Okay, see reasons. Same reason, more males are affected, and then the it skips generation. Okay, number 16, if a child has an autosomal trait, what can you say about the parents? So if it's autosomal dominant, this means that one of the parents at least would be affected. And that would be the answer to that. Okay, finally, how about calculating probabilities? When we're going to be calculating probabilities, there are three things that we need to take note of. Number one is to identify the mode of inheritance. Number two is to assign genotypes based on phenotypes that appear in the pedigree. So we will make sure that we know the genotypes. And finally, apply Mendelian inheritance in calculating probabilities, and we'll make use of the product rule here. So here's an example. We already have discussed this. So Tanisha's brother, Deshaun, has sickle cell disease. Tanisha wonders if her fetus would inherit the sickle cell allele from her. So she must calculate the chance that she is a carrier. What is the risk of the fetus, assuming that the father, Antoine, is not a carrier? So first of all, that the brother is affected and the sister is not affected. So you would expect that at least sickle cell disease is autosomal recessive. So we know that in order for Deshaun to show the disease, he must be homozygous recessive, which means one of his small a would be coming from the mom while the other one will be coming from the dad, which makes the mom and the dad as heterozygotes. So the probability that Tanisha is a heterozygote would depend. So it's possible to get X chromosome from a normal X chromosome and a normal X chromosome from the father and mother, or it is possible to get uh, a normal X chromosome and an abnormal X chromosome, which makes it possible to be either a homozygote dominant or a homozygote, a heterozygote. Okay, so computing this one, since we know that the mother and father would be heterozygotes, so we have here the biggest and the small s, the biggest and small s, and putting them together, tracing the Punnett square. So three of these would be unaffected, which would be the phenotype Tanisha. So you won't make use of the smallest, which is affected. So the probability of Tanisha is 2, since you have two possibilities of becoming heterozygote, and there are three possible combinations. So the probability of Tanisha will be 2/3. So we have 2/3 over here. Now to get the probability of the unborn child or the expected child, you have to get Antoine's probability as well. So coming from another family, it is assumed to be a big S. So we have here a heterozygote and a homozygote big S, dominant S. So we have here combining the PowerPoint, combining the Punnett square, S, biggest, and biggest, smallest. So the probability that the child would be a heterozygote is 1/2, so 2 out of 4 possibilities is 1/2. And finally, multiplying Tanisha's probability and the child's probability is 2/3 times 1/2, you will have here 1/3. So that's the probability of the child. So this ends our